Hello everyone, this is Miss Hanley, and today we're going to look at solving systems of equations by graphing. So when you're solving a system of equation, you are looking for two different linear equations, and they don't have to be linear, but we're focusing on linear equations. We're looking for two different linear equations that are either going to cross each other, and they'll intersect at a point. When this happens, you get one solution, and that means that your solution is an ordered pair, so an x, y, that's what's happening. You could have two lines that when you graph them, they end up being exactly the same line, and that's resulting in infinite solutions. Or you could have two equations that when graphed give you lines that are parallel. And if they're parallel, they're never intersecting, so you have no solution. So these are the three different scenarios that you can encounter. We're going to look at one today that has one solution. However, you can also note if you graph two lines and they're exactly the same, you should have infinite solutions. If you graph them and they're parallel, you have no solutions. And if you graph them and you have one solution, then they're actually intersecting. So let's look at the two equations that we have up here. Okay, we have y is equal to 2x plus 4, and 2x plus y is equal to 8. So the first step to graphing is to, well, usually you want to put them into slope-intercept form, your equations. You don't have to if you're comfortable graphing with x and y intercepts in standard form. That is perfectly fine. But slope-intercept form is usually more user-friendly. So I look at my first equation, y equals 2x plus 4, and that is already in slope-intercept form. And remember, that is your y is equal to mx plus b. So b is the number where you begin graphing, and m is your slope. That's how you move. B is your y-intercept. And m is your slope. When I look at my second equation, though, that one is not actually solved for y. So we want to go ahead and take care of that. If I'm isolating y, the piece I need to move away from that is 2x. And if that 2x is positive, we're subtracting it from the left and the right side of my equation. So I end up with y is equal to, since I'm looking for mx plus b, I want to put my 2x first. So I'm going to say negative 2x and then plus 8. Now I have two equations that I can easily graph on my graph. So I'm going to look at the next page here. And we have, I'll write our two equations at the top so we don't forget. Y is equal to 2x plus 4. And then y is equal to negative 2x plus 8. Now I do apologize, if you're following along on the foldable, you will have to add an extra box in order to graph your negative 2x plus 8. But on here, we will start by going up to our y-intercept for the first equation, and that would be at 4. So I'm going up 1, 2, 3, 4, and that's my first point. And then from there, we're using our rise over run. So up to the right one, or we could go down to and to the left one. So here I have my line. And it's a good idea to extend the lines pretty far across your graph. That way you actually get a chance to see where they would intersect. Alright, and then our next equation starts at positive 8. So up 5, 6, 7, 8. And then from there we're going down to and to the right one. Down to and to the right one. And so when you create your second line, you can see that these two equations are intersecting at this point right here. And on your graph, you should notice that that point is the coordinate 1, 6. Okay, so that is actually the solution to your system. Those two lines intersect at the point 1, 6. So this is a one solution problem, and that means our lines are consistent and they are independent. All right. So let's take a look at what would happen if instead of them being consistent and independent, instead of them actually crossing, they were the same equation. So maybe you have y is equal to 2x plus 4 like we began with, but your second equation is 2y is equal to 4x plus 8. Same equation, the second is just double the first. So if you were graphing that one, you could solve the second one for y, and again it's going to be the same thing. So we can go up 1, 2, 3, 4, still going up 2 and over 1, and your line is the same. It's the same line for both equations, okay? So when that happens, you have every single point on that graph is a solution to your system. So because of that, you have infinite solutions, or all solutions. And this would be called consistent and dependent, a consistent and dependent system. Okay, so when they have exactly the same, exactly the same equation in the same line, that is consistent and dependent. The last situation is if you had two equations that created parallel lines. And those two equations could have any y-intercept, but their slopes must be exactly the same. So once you figure that out and you graph both of them, you can clearly see these two lines are never going to intersect each other. They're always the same distance apart all the way along. If that happens, we have no solution. Or if you want to get really fancy, you can do the circle with the line through it. That means no solution. And so this system is inconsistent.